Alright, so we left at the end of that lecture on a cliffhanger. We said we've just found a transformation that would help us with feedback linearization for a very specific system. And we said, great. So I was able to find a transformation to change the coordinates for that other system that allowed me to put it in a form where I could do feedback linearization. But that doesn't really help me know a lot of things. So one thing is, every time I find a transformation for feedback linearization, it has to be invertible. It also has to be such that when I take derivatives in the new coordinates, that the derivatives are continuous, because the derivatives in the old coordinates should be. And so, say I find some random change of variables that I want to use. How do I know if that one meets all these requirements, like it's invertible, etc.? So, even though I still don't necessarily know, and I do not yet have any type of formula for even partially figuring out what that transformation should be, but question of, if I find one, is it going to be invertible? Is it going to have those necessary properties about differentiability? So it turns out that there's actually a theorem, or I don't know that it's a theorem, I guess there's a result, let me call it that. There's a result referred to in Khalil that says, essentially, there are some conditions you can check about Jacobians of your transformation with respect to the variables that you're doing the transformation with respect to, and non-singularity, and that you can use these to determine whether or not there exists a transformation that's invertible, or whether or not your transformation is invertible, at least locally. So essentially, the main point of this is there are results that allow people to tell if they have a transformation, is it invertible, essentially, and differentiable, at least locally. So, those requirements have something to do with the Jacobian matrix being non-singular. So, now we're going to write out the definition for when a system is input to state or feedback linearizable. So the only comment I'm going to make is that I need to define this before I write that definition. So a continuously differentiable map with a continuously differentiable inverse is known as a diffeomorphism. Diffeomorphism. So this is what we need if we do a transformation. Z is a transformation of x, and then we look in the z coordinates at the transformed system to see whether or not we can make it linear with a certain u. Then we need this transformation to be a diffeomorphism, because we need it to be a continuously differentiable map, because we're going to need to be able to take derivatives in the new coordinates, and then also it needs to have a continuously differentiable inverse as well. It does have to be invertible. So then, essentially, there's some results that say if your Jacobian matrix related to the derivative of your transformation with respect to x is non-singular at a point x0 contained in the domain of your transformation, then the inverse function theorem says that there's a neighborhood of that point such that the transformation restricted to that neighborhood is a diffeomorphism. So what you can tell is that that basically says if you can check the Jacobian matrix related to the transformation at certain points, and if it is non-singular, then you can tell that there's at least some neighborhood of that point where you would be able to have the transformation be a diffeomorphism, so continuously differentiable with a continuously differentiable inverse. So that was sort of the existence theorem I was mentioning. So now we have this definition, so now we are going to write this. So this is definition 13.1 in Khalil. So this says a nonlinear system x dot equals f of x plus g of x u. Note that we're still considering input affine, where f maps from d to r to the n, and g maps from d to r to the n by p are sufficiently smooth, meaning all the partial derivatives that are needed in any subsequent parts of results or proofs exist and are continuous on a domain D, which is a subset of R to the N, is said to be feedback linearizable. Or input to state linearizable. And this would be if there exists a diffeomorphism that's the map that's invertible and differentiable, T mapping from D to the R to the N, such that dz, which is the transformation of all the points in the domain of T, contains the origin and the change of variables continue over here. Z equals T of X transforms the system, which I'll label at 1 over here, the system x dot equals f of x plus gu, into the form z dot equals az plus b gamma of x u minus alpha of x with a, b controllable, and gamma of x non-singular for all x contained in D. So, if we think about what does that mean? Okay. So, what does this mean? What this means is that if we have this input affine nonlinear system, and we can have p inputs, and we can have n states, and if these functions that define the input affine system are sufficiently smooth on some domain, then we will call this system feedback linearizable or input state linearizable. If there is some transformation that, or some map, T, that is both continuously differentiable and has a continuously differentiable inverse, where when you, and that the domain that you get when you do the transformation contains the origin, and your change of variables, which is z of tx, makes your system go from this original nonlinear form into a form that has the structure that we talked about earlier. So the structure that we talked about earlier is that it has this linear part, and then it has this other part where the input is able to cancel out the alpha and the gamma. And then AB controllable and gamma of x non-singular, because you have to be able to take its inverse in order to cancel it with the u. So essentially, feedback linearizable systems are ones that have a very specific form where they have this original form, and then they have such a form that you're able to find an inverse to get it into the other form. So we say that if a system meets those requirements, then it's feedback linearizable. So that's really nice. So that certainly is less restrictive than where we were at earlier, where we just said, here's this set of systems where you're able to do this feedback linearization. So now we sort of expanded and we said, like, okay, as long as you can at least do a transformation of variables to get the system in that form, we'll call it feedback linearizable. However, still, it would not be expected that all the systems in the world can be put into a form like this, where you can take a transformation to get this resulting form. So this is still a restricted class of nonlinear systems. So then you could ask, like, can we make it even a little more general at least? So then the idea there would be, okay, maybe what I really want is to be a little more like undergrad chemical process control. So in undergrad chemical process control, we boil everything down to single input, single output systems. And so when we do that, we check whether or not we are stabilizing our output at the steady state value by being able to look at, for example, the poles of the transfer function. And note that in this case, what I'm really caring about in undergrad control theory is I'm caring a lot about whether or not my outputs are going to certain specific values. So am I stabilizing my output? So regardless of whether I'm stabilizing all the other states in the system, like say I have a reactor, and then maybe I want to bring my outlet concentration to a certain value, but I don't actually mind if the temperature is in some range over time, then would that make me think about this problem any differently? Or similarly, in linear systems theory, when a lot of times we have results about whether or not we're driving our outputs to zero or things like that. So how can I take advantage of maybe the fact that I don't have to look at every single state whether I'm driving it to zero? Can I do it just where maybe I look at some subset of the dynamics and I'm checking that I can develop an input that I can develop some of the dynamics to be in some type of linear form, where those are the ones that are important for determining my output, and then so that sort of my sub-linear system, the one that's related to my input to output dynamics, that one's linear, and then that I analyze whether or not my output is tracking certain values by looking at the linear systems theory. So then this is the concept of input-output linearization. So now we will put that over here. Okay. So here's an example. So going back to that one we were looking at before, essentially, here is the case that we had earlier where we said, you know what, no matter what I do with u here, I'm never going to be able to make this part linear. And we have y as x2. Now we were able to find a coordinate transformation to deal with that. But what did that coordinate transformation give us? So what we did earlier was we said, okay, take z1 as x1, take z2 is a sine x2, and take u is equal to x1 squared plus 1 over a cosine of x2 v. And then we said, look how great, like, what I did. Now let's see what my resulting system looks like. It looks like z1 dot equals z2, z2 dot equals v, and then y is in arc sine of z2 over a. So if we wanted to analyze what y is doing using linear systems theory, so here we're going to have a linear system, but it doesn't match the typical linear systems theory form. So usually when you do something with linear systems, you might have a form x dot equals ax plus bu, and then you would have y equals cx plus du. And then there's a lot of results that talk about how does a system like this behave. You can see that this system, even though this part has the form like this, but this part with y does not have the form like this. So then any results where you would require the y from linear systems theory, where you require y to have some type of linear form, that doesn't hold. So then you can say, okay, so what can I do instead? So what if instead I do this? So same thing, same system, x1 dot equals a sine x2, x2 dot equals negative x1 squared plus u, y is x2. But if I was to use this, so say I use u is x1 squared plus v. So now what I would get is, so I would still have the x1 dot be the same thing, but I would get x2 dot is v, and I would get y is x2 for that same system. So now you could say like, oh, well if all I, like, x2 here is y, and here is how x2 changes over time, and I can make this some type of linear thing, like say this is like negative x2 or something. Then I would say, oh, okay, I'm driving x2 to 0, and that means my output is being stabilized. And you could say, looking at just this part of the dynamics, I can tell very easily from linear systems theory what's going on with y. And so this is the concept of input-output linearization, is that maybe we don't need to make the full dynamics. So we still have this one. We still have x1 dot is a sine x2. We've still got this one, but here we were able to analyze things about whether the output is going to 0 and this part of the equation only using linear systems theory, but we didn't really worry about what was going on with this. Now, you do need to worry about what's going on with this, but I was able to do something about linear, sort of using linear theory. Despite that my whole system is not linear, I was able to use linear theory to analyze output tracking, but only analyzing output tracking in the presence of x1 dot remaining, you don't really care if y is going to a value if x1 dot is going crazy. So note here that if x2, for example, if you're trying to track a value x2 that's not the steady state, then x1 dot a sine x2 is going to be a value. And so if, say that you drive y to a value of 0.1 or something, so you'd get x1 dot equals a sine of 0.1, and then if y is stabilized at 0.1, you would always get x1 dot equals essentially a constant, a sine 0.1. So x1 dot then is always positive, meaning x1 is always increasing, meaning it's increasing without bound. So you do have to care what's going on here. You need this one to be sort of, I'm going to use a word that's not a technical term for this, but just to help with the thought process. Self-stabilizing is something that's not the technical term for this. But you can see what I'm saying. So the concept is the system here is input-output linearizable, because I was able to find an input that caused the dynamics related to the relationship between my input and my output to be linear. But then I didn't linearize the whole thing, so then I have this concept of, well, what about the rest of the system? Is something weird happening? And then so it leads to a concept of that we need to require certain things in what we call the zero dynamics. So that's related to the part of the dynamics that aren't covered in the input-output linearization, the part that does not get linearized. So this leads us to input-output linearization. So that will cover that. Now we're going to do input-output linearization. So now we'll again look at single input, single output systems. Or sorry, not again. Now we'll look at single input, single output. We were looking at multi-input, multi-output in some sense earlier when we were just thinking about the ideas of could you write a nonlinear system in a linear systems form? It will be in a linear form if you have multiple input, multiple output. Now, what we will do in order to look at this case with input-output linearization, we're going to focus on single input, single output. So right now, the first part of the way that input-output linearization goes is going to feel really random, but it's going to tie back in just a minute. There just has to be some notational stuff where it's going to feel like I don't really exactly see where this is headed, like defining all these lead derivatives, but you'll see in a minute. So the first thing that I'm going to do, again, I'm going to seem very unmotivated for a minute, I'm going to differentiate this output. So this will then be y dot, so the time derivative of y, dy dt. And so this is gotta use the chain rule, because y is a function of x is a function of t. So y dot is dh over dx times f of x plus g of x u, defined as equal to LFH plus LGH u. So, okay, this part I think we can see as the chain rule. What the heck is this? This is just what we call the lead derivative. This is just purely notation. Literally, LFH of x is defined as me being dh over dxf. And so this is the concept of the Lie derivative of h with respect to f or along f. This is the concept of the derivative of h along the trajectory of f. You can define more and more of them. You can do Lg LFH of x is equal to the derivative of LFH dx g. So you can see that it's this last one is the one that's over here, and then these other things are the things that are being derivatives with respect to x. And you'll see that again if we do LF squared h of x, which is LF h of x, which you can see here then, pattern is, we just said that the last f gets put over here, and this part is the differentiation. So dLF h over dx, and then the f. So you can see the pattern developing. We can keep going. We can do another one. The next one is LF k h of x equals LF k minus 1 h of x. So pattern was, we put this part, take its derivative with respect to x, so this will be d LF k minus 1 h of x over dx f of x. And so one more, LF 0 of h of x is just going to be h of x. So you can see the pattern developing. You can see how you would do this. Okay, so that seems really random for me to have just defined a lot of Lie derivatives. Don't worry, you'll see in a minute. Next part that also seems really random is the other part that I'm going to do now. So the other part that we're going to do now is going to be that we are going to say y dot. Okay, going back to our y dot is defined as equal to the LFH plus LGHU. So remember that this came from the derivative of h with respect to x times f. This was the derivative of h with respect to x times g. So now, more stuff where you're going to be like, where is this going? But believe me, it will make sense in a minute. So if LGH is not 0, what can we say? So if LGH is not 0, what we can say is that the u now appears on the right-hand side of y dot. Now, then essentially what I just said. Okay, but now say LGH is equal to 0. So now if LGH is equal to 0, then what we get is we just get y dot is LFH. So now y dot has no dependence on u. So we could then say like, okay, so essentially the input doesn't affect the first derivative of y. So we can say, does the input affect the second derivative of y? So then you can say, oh, okay, let me differentiate a second time. So here I'm going to say y2 is d. So remember that if LGH is 0, y dot is only this LFH part. So it doesn't have this u. So then that's why I'm going to do this. So it's going to be the derivative of this y dot, so which is LFH, with respect to x times x dot again. So it'll be times the f of x plus g of x u. So what this is going to give us is this is going to give us LF squared based on the notation that we just said. So I said I defined that notation for a reason, even though you still can't really tell why I'm doing what I'm doing right here, but now you can say, oh, at least I see why she had that notation. So here's the second derivative. Okay, so then we can analyze this again. We can say, oh, okay, so does the second derivative depend on u? So then we can say, okay, if this part is 0, then the answer is no. If this part is not 0, then the answer is yes, then the input's right there. So you can keep going and going and going, just like the Energized Bunny. And then we can say, okay, eventually, if we keep doing this and doing this and doing this and doing this, what you would get, and you can prove this to yourself on paper if it helps you, or if you see it, fantastic. But you can go and go and go and go. And eventually, you'll get that if LG LF of I minus 1 h of x is 0 for I is 1, 2, rho minus 1, but LG LF rho minus 1 h of x is not 0, then u is not in y dot 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 y rho minus 1, where this means the like rho minus 1 derivative of y, but is in y rho with a non-zero coefficient. With a non-zero coefficient. So then I'm going to write this, so then this means that y rho, the roth derivative of y, is equal to LF rho h of x plus LG LF rho minus 1 h of x u. So then that's what you can see up here. You can see that when this one is not 0, which is this guy, then now finally you have your input impacting the derivative of y. So then you can say like, how is that related to anything? Okay, so that is a super question. So, really quick then, let me write out what this was related to. So, we are looking at input-output linearizable systems, and what we said is that the case where we would call it input-output linearizable is that if we can find a transformation that gives us this kind of system, u minus alpha of z, with y equals cz. So if we can at least make some of the dynamics behave according to this, where the u is able to cause nonlinearities to cancel out in these z coordinates, and to give you a linear system in whatever part of your dynamics are related to z, and that your output not only depends on z, but that it depends on it in a linear way. So even if you have other dynamics, like we said earlier, even if there's some other stuff going on, but if you can do this to part of your dynamics, so importantly, that you're able to make the z1s have it so that you can choose a u that will linearize the z dynamics, and that only the z dynamics are important in determining y, and that the way that y depends on those is linear. If you can do this, then we say, okay, look, it's input-output linearizable. So the question is, a lot of times in chemical engineering, you're not going to have any process that obviously looks like this. So then you're going to say, okay, so how can I bring my original system to this form? So there's going to be a way to try to a little bit systematically look at that. So say that my original system has this. It has h of x. It has y equals h of x. So here's my original system. It's an x. It has y is h of x. And then I'm going to just write these. So this is what we just said. We said LFH of x is the first derivative if no output appears. So you keep going and going. You could say like, okay, so if the output does not, or sorry, if the input does not appear. If the input does not appear on the right-hand side of my first derivative, then I take the second derivative. And then if the input does not appear there on the right-hand side, then this is what I'm left with. And I keep going and going until I do this y rho, which then we say like, oh, great. Here's the one where finally it appears. So I mean, this could be the first, this could be the second, rho could be one of those. If you have plus the term times u, then you can stop there. But if you don't have it in the first, you don't have it in the second, keep going until you get finally to one that will have this form. And now it finally has the input on the right-hand side. So then we can say like, oh, okay, cool. So that was what we just did a minute ago. Now we have to relate that to this problem. So think about this idea. Let me call y here, h of x. Let me call this z1 bar. Then let me call this one, say like, oh, this is the derivative of y. So this is actually z1 bar dot, because it's the derivative of y, and I'm going to call this z2. Now, this one here is the derivative of y1, so it's the derivative of z2. So this is, sorry, this is z2 bar. This is z2 bar dot, and I'm going to call this z3. And you can keep going and going like that. And so, essentially, in the end, you get down here, you get z, so when you finally get there, it will be z dot rho is equal to this LF rho h of x plus LG LF rho minus 1 h of x u. And you'll say like, oh, interesting. This u, I could actually cancel out the nonlinear parts here by selecting u is 1 over lg lf rho minus 1 h of x to the negative lf rho h of x plus the v. Again, the v is where you can choose that to linearize your new dynamics. So you can say, oh, weird. So what does this, like that kind of looks like the form of the system, but I'm getting this to be like, each of these, this derivative has a linear dependence on z2, and this derivative has a linear dependence on z3, and this one, until I keep going, it will be, why do we keep leaving up the bar? There will be a linear dependence on all these variables until I get to the final one, and then we'll have that nonlinear dependence, but it doesn't matter because it's cancelable. So we're like, oh, that seems to be the input-output linearizable form. And then you say, you're correct. You have seen the explode. Then you have realized the reason that we did this. And so, in the end, you would be able to do something like this. You would get a system where you have something like z1 dot is equal to z2 bar. Z2 bar dot equals z3 bar. And then dot dot dot. Z dot rho is equal to v when you plug in the u that's down here. And then you can say also my y equals z1, because that was how we defined it. And then so we say like, hey, look at that. I was able to get linear dynamics in the adjusted coordinates. Now I'm going to choose v so that I make the eigenvalues of this resulting linear system be negative. And look, feedback linearizable. Linear relationship between y and z1. Linear up here. All the requirements got met. So that was why we did this, is because this provides a somewhat systematic method for dealing with finding what are part of the dynamics of an input-output linearizable system and what's the transformation that you need. So you can see that this defines part of a transformation. So let me just do one definition really quick. So the row that you get here, where you say the roth derivative, when the roth derivative of y depends on u, then we call that the relative degree of the system. So as a quick example, let's see where we define the relative degree. Then you would get something like this. So say that we have x dot, oh, that's just definition of relative degree. X1 dot equals x2. So your relative degree is not necessarily existing, and it is not necessarily well defined everywhere. So and it does depend on your output, so it's output dependent. So x1 dot equals x2, and we can say x2 dot equals negative x1 plus epsilon times 1 minus x1 squared, x2 plus u, and then for some epsilon greater than 0. So if we choose two different y's, we have two different relative degrees for this system, and they can be defined on an interval. Or if we choose three different y's. So say we do y is x1, then what we get is that y dot is x1 dot is x2. Then we get y double dot is x2 dot is negative x1 plus epsilon times 1 minus x1 squared, x2 plus u. So look, if we look at this, we say in the first derivative of the output, we do not have the input. In the second derivative of the output, we have the input. This means that the system has relative degree 2. We can see that it always has the u on the right-hand side, so this is actually relative degree 2 in R2. Now, as I said, the input is important, the output is important. So if I change the output, I have a different relative degree, because the relative degree is related to how many derivatives of the output do I need before the input appears on the right-hand side. So then we can try another one. We can try y is x2, and then we can say like, okay, so I'm going to take y dot is now negative x1 plus epsilon times 1 minus x1 squared x2 plus u. Oh, okay, look at that. Now I have the derivative is already on the right-hand side for just the first derivative. So we can say that the system has relative degree 1 and R2. And so I think this is a good example because this can make you think about actually this sort of structure is a little bit like the structure that you have for the CSTR, for the nonlinear superparabolic CSTR with say that you have a heat rate input Q, and then that pretend that that's your only input. And then so you have whatever you have for CA, there'll be some more complex differential equation. But if you think about this, CA depends on temperature if you use an Arrhenius rate law, or CA dot depends on temperature if you use the Arrhenius rate law. So the second derivative of concentration would have the Q in it because that's where the derivative of temperature would come in. But the derivative of concentration itself does not actually have Q in it. But the derivative of the heat rate includes Q. So if you're wondering what is sort of the physical meaning of the relative degree, this is not an exact statement, but you can think of it as to some extent representing the fastness or connectedness between an input and an output. So if your output is temperature, for example, and your input is the heat rate, then that would be sort of this case, where your first derivative of temperature already includes the input. So when you adjust the input, you already are adjusting the first derivative of your temperature. So that means, versus if you are trying to adjust concentration and you're trying to do it through the heat rate, then you won't be able to make a difference in the first derivative. You'll make a difference starting at the level of the second derivative. And I think as a chemical engineer, your general thought would be like, yeah, if I'm going to control the temperature, I probably am going to use the heat rate. But if I'm going to control concentration, I don't know that heat rate is the way that I would exactly do that. I mean, that seems a little loosely like related. And so then you could say like, well, you could think of relative degree as to some extent showing you that intuition that you already have. Like, yeah, the temperature is more related to the heat rate than concentration is related to the heat rate in the sense that if you change the constant or if you change the heat rate, you sort of have a sense that that is a that makes sense for me to do if I'm trying to get temperature to go to a certain value, but to get concentration to go to a certain value, I might prefer to choose something like the inlet concentration because you have just a sense that that might work faster. And your sense of it working faster is probably the sense in which if you change concentration through the heat rate, it actually is a second derivative of the concentration at which you will start to see the impact of the heat rate. And then versus if you change instead like inlet concentration in order to change the concentration, that will be in the first derivative. So then the idea here is just like you have a sense already of relative degree and its importance, but this kind of formalizes the concept of just how many derivatives of the output do you have to take before you get the input to appear. And so you can imagine that if you have to take many, many, many derivatives of your output, you start feeling like maybe there seems to be a little bit of a weaker dependence between my output and my input. Maybe this isn't the best input-output relationship. And especially if you have no well-defined relative degree, so essentially your input never affects your output, then you would say this really is not an input-output pairing that makes basically any sense because the input that I'm using to try to adjust my output does not impact my output ever. But let's look then at finishing this off. So, as I said, you also could have like your relative degree be defined to a region. So y is x1 plus x2 squared. Y dot then is x2. This is for the same system we were just looking at. Plus 2x2 times negative x1 plus epsilon times 1 minus x1 squared. X2 plus u. So the relative degree is when when the u actually appears on the right-hand side. So in this case, the u does appear except when x2 is 0, because then this whole term goes away and the u also goes away. So we say it has relative degree 1, but in a restricted domain. So it's in this domain where x is in R2 and x2 is not equal to 0. Because when it's equal to 0, then the u goes away. And then so the one that I was mentioning a minute ago, what happens if you have not a well-defined relative degree? Then x1 dot is x1, x2 dot is x2 plus u, and then y is x1, and y dot is x1 dot is x1 is y. So this is what you can see here. So weird thing, right? When y is x1 for this system, y dot is x1 dot is x1 is y. And so that's the same thing we had before. So no matter how many derivatives you take of this y, you're always going to apparently get back just x1. And then, so you're never ever going to get u on the right-hand side because you always get the same derivative every time and it never includes u. So this system actually does not have a well-defined relative degree. And then, so again, going back to the physical meaning, if you think about that, that means that, like essentially, this is evolving completely independently of u. This is doing whatever it wants, and as you can even see in this example, there is nothing that you can do with u to ever impact x1. x1 is unimpacted by u. So there you go. So then just the idea of, okay, so can I make this any more? So that defines relative degree, and that helps you understand that. But we're still trying to talk about input-output linearization. So let's go back to input-output linearization. So we have our system. So again, we're looking at single input, single output. So x dot equals f of x plus g of x u. And then we have y is h of x. So here, SISO, single input, single output. So for the SISO system, we want to say, okay, can I figure out a transformation for the system that will then give me a linear dynamics related to at least some of the states and my output, so that I can analyze essentially output tracking with linear systems theory. And then the rest of the states be something. And then, so we're trying to find that transformation that does that. So Z here is our transformation, and it turns out that we can a little bit be specific about what we would like. So we want to see, so Y is T of X, then this is going to be, here is the transformation that you can use to make this happen. So phi1, phi n minus rho of X, then we have h of x, LF rho minus 1 h of x. So here's the transformation I already mentioned earlier, the one where I was like, oh yeah, because this is, you'll call z1 equals y1, and then dot dot dot, and then so this will be the 0 dot will be the derivative of this, which will start to give you u in the right hand side. So this is a transformation that we can get, and so this is going to be phi of x, and then psi of x, and this is going to be defined as equal to eta. We're going to split up our states. We're going to call them eta, and I'm going to call this zeta. And then, so we're going to call these set of states, we're going to call these eta. We're going to call these set of states, we're going to call them zeta. So then this is the transformation we want to choose, but we do want to put one additional requirement on it. So we know that this part, because we already said this earlier, that when we take the derivative of all these zeta states, it's going to give us the linear part that we need. But then we do want to make one more requirement about what's up here. So we do want to have where the phi1 phi n minus rho are chosen such that T of x is a diffeomorphism, so that's important. We need to make sure that whatever we choose for the remaining transformation, we're still able to have a continuously differentiable map with a continuously differentiable inverse. So this is a diffeomorphism on some domain that's a subset of D. And then, so here's the other requirement, and d phi I over dx g of x is 0 for 1 less than or equal to I less than or equal to n minus rho for all x contained in D0. So then you could say, what the heck? Why do I care about that last part? What is that? How does that relate to anything? Well, the answer is this. If we go through and we write out, oh, I don't know what's going on this part of the board. It's so hard over here to erase. So if we go through and we write out, let me not do it over there. I think that's hurting. So the answer is this. So if we go through and we write out what the derivative of our states is, so in this transform coordinates we get z1 dot, z2 dot, so let's just let go, dot dot dot, z dot, n minus rho, and then we got z dot, n minus rho plus 1, dot dot dot, z dot rho. So in the way that they just defined the coordinates, these first ones up here are the ones that were the derivatives of the phis. So for the phis, we're going to get stuff like d phi 1 over dx, and then dx dt. So that's going to be f of x plus g of x u. And then we're going to have like all the other ones down to here, and then we're going to get the ones down here, the ones that are like lf, h, dot, 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 until we get the last one where it's going to give us something that has a u appear in the right type of form for us to be able to then linearize this part down here. So the reason that we cared about those derivatives of the phi is because if you look up here, all of these derivatives of the phi, so this is going to be phi 1, then you'll have this for all the phis until n minus rho. If d phi 1 over dxg is not 0, which is the requirement that we're making, if that's not 0, then whenever we do the linearization down here with the u to try to linearize the input-output dynamics, we're also affecting the dynamics up here. That gets kind of confusing from a stabilizing perspective because the whole goal of this was to be able to like stabilize this part and then feel confident about what's going on up here. And so if whatever we choose to stabilize this part, if we also impact this part, then every time we choose a different u, so you know how we have u equals something, something, something plus v or whatever. So every time we change v, we have to then go back here and analyze, did that v, or does that u, which includes v, does that specific v and that specific u choice cause this up here, these dynamics, to somehow be stable, because I can't just let these go off to like infinity while I stabilize my output. I have to make sure these are also remaining stable. So the idea with d phi I over dxg equals 0 is that you want that transformation, because then you can do whatever you want to the u down here. You can choose whatever v you want. You can choose whatever u to stabilize the input-output part, or I guess the part that relates the input and the output, where the part that linearizes those dynamics. And then up here with everything else, you can just, as long as you find the transformation where d phi 1 over dx is g is 0, then you're fine if you can analyze this part essentially independently before you worry about what is your u and your v. So that's the motivation for that. And then so a good question would be, so can I find transformations that have that really weird kind of very specific property? And then so there is a theorem that says that, like, yeah, basically. So I'm going to write the theorem. So consider, consider the system. I'll come back to this in a minute with a better pen.